Hello, I'm Sue Nelson, and on today's Planet Earth podcast, we bring you an update on a space mission that's examining the salinity of our oceans and why scientists are using a great big radar dish to track insects.
Usually they're rather small ones, just about the size of a green fly, and in fact it's better to have the small ones because you don't want the big ones that might be flying under their own steam. You want them just to be floating around following the air.
More on that story later. I'm surrounded by fields and the Hampshire countryside at the moment at the Chilbolton facility for atmospheric and radio research beside an enormous white antenna. It's more commonly known as the Big Dish by those who work here, and I'm joined by the facility's head, Charles Wrench. Charles, how big is this dish?
This dish is 25 metres diameter. And it's fully steerable, which means that we can scan it in both elevation and azimuth to track storms or clouds as required by the researchers who come to use the facility.
How easy is it to actually steer? You say fully steerable, but I can't imagine how you would actually begin to steer something of this magnitude and height, because I don't want to go all Superman on us, but I mean that's like a sort of 10-storey building or something. It's probably not that big, but it's very difficult to gauge heights.
Yes, it is a big structure. It was originally designed for radio astronomy, therefore you have to point very accurately, in fact pinpoint accuracy. We don't use it for that purpose right now. We're using it for meteorological research, but with computer control in the control room, we have our radar scientist who is just about to actually start it up for us, and you'll be able to hear the system operating. That's the klaxon to warn anybody outside that the dish is about to start moving. We're now doing an azimuth scan, so it's a fixed angle of elevation, and it's going to rotate through 360 degrees.
That's amazing because it's very smooth. I mean, we heard a slight sort of frictional screech of a startup.
The brakes letting go. The brakes let go, but now it is actually very quiet. We've recently had the servo system upgraded. Before that, it sounded a lot more impressive, a lot more noisy, but now it's very quiet, very smooth.
It's turned through now. This enormous dish has turned through in the time that we've been chatting. It's now coming up to probably 60, 70 degrees. So in a very short period of time, it will be at 90 degrees.
It does actually rotate at 1 degree per second. So a 360 degree scan will take you 6 minutes.
Well, as it's scanning round now, this enormous dish looking out across the Hampshire countryside, let's just go into, Charles, what sort of technology you're using here. Obviously an enormous antenna like this. There's a squish there.
The antenna is a very large structure. There is a multi-parameter 3 gigahertz radar on the dish, and with that radar we're able to characterize in great detail the structure of storms, precipitation, convective storms. With that radar we have a 0.25 degree beam, and that's a very narrow pencil beam, and it means that we can move it around within the convective storms, and we can look at the structure going on within those storms.
So you're bouncing off effectively then
a
radio wave, a beam on clouds, that the sort of clouds that are above us today.
Yeah, we're transmitting pulses of radio wave energy, wavelength of about 10 centimetres. And what's happening is those pulses of energy are being transmitted out into the sky. They're finding targets, and you're getting a small amount of power reflected back. We're actually diagnosing how that power looks when it returns to us, and so that we can then establish particle sizes, particle types, particle phase, i.e. are they ice, are they liquid, within storms or clouds.
Now I can see as the dish now is facing us, you can see that there's sort of almost looks like a porter cabin in the centre, sort of held out by 4 arms in front of the dish. What's inside that
That's
porter
a very
cabin?
good description. That's the focus cabin, and that's at the prime focus of the parabolic dish, and in there we have the receiving horn and the front end of our radar receiver. So basically the signals are generated in the control room, they're fed through waveguide and cables up to that porter cabin, into a feed horn, then they're directed at the surface of the dish, they're transmitted, and then the signals come back, or much reduced signals come back, and the reverse happens. They're picked up by that feed horn into the receiver and then fed through waveguide back into the control room.
You've also got, I noticed, just in front of the glass-fronted control room, you've got a smaller dish. I mean, that one is only a metre or two across. So how many other dishes do you have around the site?
That is a dish on a higher frequency radar. That's a 35 gigahertz radar. That's designed specifically for looking at cloud structures. We use higher frequencies for clouds because the particles within clouds are smaller, and therefore you need a shorter wavelength to detect them effectively. In terms of dishes on the site, I think we've probably got 3 of that type.
And what about behind it? Because when I arrived, behind there was a sort of even smaller dish and what looked like a plastic owl.
Right. Yes, indeed, that is a plastic owl. We have a multi-frequency microwave radiometer, which is measuring energy coming down from the sky. And we use that radiometer for measuring water vapour profiles in the atmosphere and the liquid water content of cloud. You mentioned the plastic owl. The owl is doing a very good job protecting the instrument from the attack of birds in the vicinity.
I love it. I love the way the most simplest of things can actually protect such important scientific equipment.
Very, very, very cost effective.
Excellent. Well, as scientists from across the UK work here, I went to see Anthony Illingworth at the University of Reading, who uses the big dish here at Chilbolton to track insects.
Well, we're standing outside the Department of Meteorology, and you can see it's a bit of a sort of showery day today. There are some nice cumulus clouds around, and there's a few showers around. And this is the work we're involved with, really, is trying to improve the forecasting of thunderstorms in the summer. And of course it's these convective storms that break out locally and give severe flooding locally in some areas but not in others. And at the moment the forecasts are quite good in the summer, saying, well, today we're expecting widespread thunderstorms over southern England, but that's not terribly useful for people because you can't really do much about it, because maybe it'll be in Oxford or Basingstoke or Southampton. So what you'd really like to know is 4 or 5 hours in advance, say in the middle of the morning, is the thunderstorm likely to be in one place or another? Particularly if it's going to be a severe storm that could produce flooding, and you're reasonably certain it's going to be severe, then that 2 or 3 hours enables you to take some mitigation activity. At the moment, we can measure where it's raining very accurately using radars. So there's a whole network of weather radars over the UK, about every 100 kilometres or so, and they sweep around their beam at low level and get a reflection from the rain. So they see the rain, but of course by the time it started raining in the afternoon, it's too late.
See, we already know it's raining,
Yes.
yeah.
So you'd like really in the morning to know where it looks as if it might rain. And of course in the summer what happens is you get the air in the surface layer starts to converge, and in some area that's preferred, then the air converges, and when it meets it goes up, and that's where your storm's going to form a couple of hours later.
So how do you find out then in advance where these two streams of air are sort of going to converge and produce this summer thunderstorm?
Well, you need some sort of tracer in the air. So the radars themselves, which you've had for many years, are designed to see raindrops. But if you look very, very carefully, really down in the noise, you can actually see the return from insects.
So you're saying as we look above us now, there are some grey, very grey clouds, some wispy white clouds, that inside those clouds are plenty of insects?
No, it's in the clear air before the clouds formed. In the lowest few hundred metres is where there are insects. There's just enough of them, and they float around with the wind. So by looking at with the radar, which of course is Doppler, we can tell whether the wind's coming towards us or away from us. So this is before the clouds have formed in the lower levels of the atmosphere, where the air's being heated up and it's starting to move and convect. It enables you to see where the convection is a maximum and where maybe in a couple of hours later you use this wind information and feed it into the operational forecasts, which are now run at very high resolution. And if you can tell what the wind structure is on the scale of a few kilometres, then you can feed that into the model. Forecasting models run with a kilometre resolution over the whole of the UK, so they're capable of telling you where storms are likely to form. But of course they need some data in the morning to know what the winds are doing. And then you can put that into the model, and it says, there'll be a severe storm, say in Oxford or Basingstoke, or a little bit more specific than we could do it at the moment.
These are all sorts of insects, flies, wasps, any type.
Usually they're rather small ones, just about the size of a green fly. And in fact, it's better to have the small ones because you don't want the big ones that might be flying under their own steam. You want them just to be floating around following the air, which is what most of them are doing, actually.
So are you effectively looking for two opposing columns of moving insects to see where they're going to collide, and then that will enable you to forecast where there's going to be a storm?
Well, we can see the insects actually out to about 20 kilometres from the radar, and they're usually in the lowest couple of hundred metres, so we're looking at the surface air. So when the sun starts to shine on a summer's morning, then the air starts to move and be convected, and we're looking for areas where the air is sort of converging towards one spot. And if we see all the winds pointing to one area, and of course when the winds meet, then the air has to go up, and then that'll form a cloud, and that's where you're likely to initiate your thunderstorms.
And how accurate is it?
We'll have to come back in a couple of years there because this is still experimental. We developed this, of course, first of all, using that very big dish at Chilbolton in a research mode. Now we're testing it out on the network of radars that run 24 hours a day around Britain, day and night, measuring basically rain, but we also have this technique for seeing those insects in there and how the insects are floating around and how the air is moving because the insects are being pushed around by the air.
Anthony Illingworth from the University of Reading, who uses the big dish, that 25-metre antenna here at Chilbolton. Charles Wrench, how important is the work that goes on here?
The data we collect here is very important and will continue to be very important. We're collecting data for most of the instruments all the time, 24 hours a day, which means we're collecting details of the clouds that pass overhead. We're collecting the depth of the cloud, the height above the site, and also information about the particles within those clouds. That is very useful for the research community that can then take that data forward and improve their forecasting of where clouds will appear. So it's important for improved weather prediction and eventually improved climate prediction as well. Additionally, the fact that these instruments are running 24 hours a day means that we can capture unexpected events. A classic example of this was the volcanic eruption from Iceland last year. We were online, we were operating, and we were able to make early observations of the ash plumes as they passed over the site.
Charles Wrench, thank you very much. You're listening to the Planet Earth podcast. Now we know why clouds are measured and how tracking insects can improve forecasting summer storms and flooding. So we continue our water-related theme with an update on SOMOS, the Soil Moisture and Ocean Salinity Satellite. Launched in November 2009, the soil moisture part of the mission recently took centre stage during the floods in Australia, as SOMOS's satellite data helps show the extent of saturated soil in Queensland and when runoff or flooding was likely to occur. Mapping the saltiness of the ocean also has important applications. The Earth's climate is largely determined by ocean circulation, and salinity plays a key role. To get an update on the SOMOS mission, I visited Merrick Shrokos at the National Oceanography Centre, Southampton, and he began by reminding me why understanding the ocean's salinity is so vital.
Well, the importance is that the density of the ocean is determined by the temperature of the water and the salt content of the water, and the density structure of the ocean influences the currents. So in the North Atlantic, what's happening is warm, salty water is moving north towards Greenland and Iceland. And as the weather systems cross the Atlantic, they take heat out of the ocean. So the water gets colder and denser, sinks and comes back as a deep, cold current. And we have what's called the overturning circulation. And that's an important part of the global ocean circulation, moving heat northwards. It gives us our temperate climate because the atmosphere is taking heat out of the ocean. The salt content is changing. Say you had more rainfall and the ocean became less salty as the heat was taken out, as the water moves north. If it was less salty, the water might not sink, so you could actually change the circulation patterns, change the amount of heat that's coming towards the UK in the ocean and then into the atmosphere. So you could change our climate. So it's important for understanding how the ocean works and then how the ocean is related to the atmosphere and therefore to the climate and what we experience as human beings. Clearly those effects we're talking about long term over years and decades rather than your weather pattern tomorrow.
What's the advantage of measuring salinity from a satellite as opposed to doing it using a sensor or a buoy or some sort of instrument that would go from a ship right by the ocean? Because you'd always think that, being there at the time would give you a more accurate result than doing it from several hundred kilometres above the Earth.
You're quite right. You can make a much more accurate measurement from a ship or from a buoy. The trouble with a ship and a buoy is you get a measurement at a specific point in time and space, and you don't get the coverage globally that you're getting from the satellite. That's primarily why we've gone to satellite data for the oceans, is that you can get a global picture very quickly. Over 2 or 3 days, the satellite can map the entire ocean surface. If you tried doing that with ships, it took a very long time. And even with the Argo buoy system, where we have 3,000 buoys floating around the ocean, that's only a buoy every 300-400 kilometres. So the sampling is still fairly sparse, and the satellite can sample the entire ocean quickly.
Scientists have now produced a salinity map of the Earth's oceans, showing the saltiest areas in red and freshwater regions in blue.
We can see that in the what's called subtropical gyre regions, where the evaporative effects in the ocean, so you're losing fresh water into the atmosphere through evaporation, so you're increasing the saltiness of the water. You can see that that's more salty. And then if you go towards the equator, where you have higher rainfall and therefore you're adding fresh water and decreasing the saltiness of the surface ocean, you can see that it's less salty. So you can see the patterns that we know are there from previous measurements, but we're getting that information now every few days rather than having to accumulate it over many months and years of ship measurements.
And for scientists working on the mission, it's an important step towards a better understanding of our oceans and climate.
I guess our achievement is twofold, really, that we have measured salinity from space for the first time, and we are able to now start mapping salinity on a global scale from space.
Merrick Shrokos from the National Oceanography Centre, Southampton, ending today's Planet Earth podcast from the Chilbolton Facility for Atmospheric and Radio Research. Do check out our Planet Earth online website, where you can find all our past editions on the site. And get in touch with us on our Facebook page, where you can also see a video of that 25-metre fully steerable big dish in action. See you soon.